Okay, so we've been talking about torque and static equilibrium, and I just wanted to review one of the questions we had done in class. This is example 2 from your notes, and it's a classic ladder problem. Okay, so we'll read the question first. A 5-meter long uniform ladder leans against a wall at a point 4 meters above the ground as shown. A 55-kilogram painter stands 3 meters up the ladder, which has a mass of 12 kilograms. Assuming the wall is frictionless but the ground is not, determine the forces exerted on the ladder by the ground and the wall. As in every question, you should look at all the numbers that have been given in the question. We know the ladder is 5 meters long. That the ladder, is 4 meters against a wall. You've got a 55-kilogram painter 3 meters up the ladder. You have the mass of the ladder. Torque questions have other words that are very important. When you see something like a uniform ladder, you have to know what the uniform means. It is telling us that one area is frictionless, but one area is not. And we have been asked to find forces exerted on the ladder by the ground and the wall. So torque is very similar to F-net statements in that you need a free body diagram before you can do your torque net statement. So we're going to redraw the free body diagram first. Alright, so you have a ladder leaning against a wall. We know that there's a person on the ladder, so that will provide a force of gravity. And we'll call that force of gravity P for person. Now, the first sentence, a 5-meter long uniform ladder. The word uniform means the center of mass of the ladder is at the center of the ladder. So we have another force of gravity, and that is for the ladder. Now, any object that touches the surface has a normal force. So a ladder is going to touch the surface at the ground and at the wall. So there are actually two normal forces for ladder problems. Force normal at the ground and force normal at the wall. So you have to recall that definition of normal force is when a surface is pushing back. It's part of Newton's third law, and a normal force is always perpendicular to the surface. The word normal means perpendicular. Now, the last and the final group of forces we have to consider, assuming the wall is frictionless, so there's no friction at the wall, but the ground is not. So there is a force of static friction at the ground. The ladder is not moving, the ladder is in static equilibrium. So if you were to consider, okay, if there was no friction, what way would the ladder move? So the ladder would slip. It would slip out this way. Now, friction would have to be in the opposite direction to hold the ladder inward. So we'll call that Fs for force of static friction. Now, the diagram gets a bit cluttered in terms of all the forces, but as you know, we're going to simplify the forces that we're using in the question by choosing our pivot point. As with any torque problem, you need to get a list of givens. And for torque, the definition of torque is Rf sine theta. So for every force in the diagram that contributes to the torque, you have 3 givens. R is the lever arm, F is the force, and theta is the angle between R and F. So we go back to our diagram. And for ladder problems, you can see this ladder problem is actually a little bit more difficult than other ladder problems because the angle has not been given. So this is an extra step that you usually wouldn't see in a regular everyday ladder problem. So I'm just going to draw a triangle which will represent our ladder. The ladder is 5 meters long and it is 4 meters against a wall. Now a wall and the ground makes a 90-degree angle to each other. So now this is reduced to a simple math problem from grade 9 or 10, where you have a right triangle, you have one leg, and you have a hypotenuse. So you look at the angle that we're looking for, the side we have is the opposite side, and we have the hypotenuse, and you would find your angle using trig. Sine theta is opposite over hypotenuse. So we have sine theta is 4 over 5. Or theta is the inverse sine of 4 divided by 5. it for our free body diagram. For all of these forces, we need the angle that the force makes, and we need the distance. So if this angle is 53, and I'll erase this, but the alternate interior angles, this line and this line are parallel to each other. So you can see the Z shape you're familiar with in math. So this angle is also 53. Okay? Okay. Now, the last and final angles that we'll have to look at are the force of gravity. What angle does the force of gravity make with the ladder? So, gravity is obviously perpendicular to the ground. Okay? Now we have a smaller triangle where we have a 90 and a 53. So all the angles of a triangle have to add up to 180. We have a 90 and a 53, which means we have 37 degrees left over for both of those. So here's how the ladder problem is different than other torque problems you've done. The angles are never the same. The angle at the ground is always going to be different than the angle that any vertical force makes with the ladder. All right? So now we're ready to set up our list of givens. Okay? R1, F1, theta 1. So we identify what is going to be the first force that causes the torsional or torque effect on the ladder. Well, look at how many forces we have. There are 5. How many do we currently know? We don't know any of them, but we do know the mass of the ladder, and we do know the mass of the person. So we have the ability right now to find 2 out of the 5 forces. That's not very much. So we have 3 unknown forces. This is where the choice of the placement of your pivot comes in. You have to pick a pivot point to get rid of either this force that we don't know, or to get rid of these 2 forces that we don't know. Let's choose the pivot point incorrectly. If we put the pivot point here, and we attempted to do a torque net statement, there are still 2 unknowns. You do not know friction, and you do not know the normal force at the ground. So you have to, there's only one choice to put the pivot point at the ground for this question. Now we are left with 1 unknown. Forces at the pivot point do not cause a torque or a rotational effect. So, our first force, we'll read the diagram from left to right. We have force number 1 is the force gravity of the ladder. Force number 2 is force gravity of the person. And force number 3 is force normal of the wall. So again, it's a uniform ladder. So the uniform ladder, that means it's halfway. The lever arm is halfway up the ladder. mg will be the force that the ladder itself, force of gravity of the ladder. So the ladder has a mass of 12. So we have 12 times 9.8. And the angle we've identified is 37 degrees. So 117.6. So that's one of our forces. We have all the information we need. So now we go to force of gravity of our painter. And our painter is 55 kilograms. From the original diagram, the painter is 3 meters up the wall. So we have R2, 3 meters from the pivot. F2 is going to be mg of the painter. That one's of the ladder. So we have 55 times 9.8. And theta again is the same as the force of gravity that the ladder had. So we have 55 times 9.8, 539 newtons. Okay, so there's 2 torques taken care of. We've got 1 left. R3, F3, theta 3. Alright, so the ladder itself, the distance, the normal force from the wall is the full length of the ladder, so that's 5 meters. And again, with the corresponding interior angles, 53 degrees is the angle, and our only unknown then would be force normal of the wall. Okay, so what you need to do next is determine, when you write your torque net statement, which forces are counterclockwise and which forces produce a clockwise torque. So if you use your pen or pencil, okay, and you hold it at the pivot point, you have 2 forces that are pulling down. So 2 of those forces, the 2 forces of gravity, force 1 and force 2, would produce a clockwise torque, whereas torque 3, which is this direction, would produce a counterclockwise torque. Now the ladder's not moving, but we need to find out what the normal force has to be such that there is no rotational motion. We are setting up a torque net statement, very similar to an F net statement. Instead of assigning positives and negatives to up and down, you assign positives and negatives to clockwise and counterclockwise. So torque 1, which is force of gravity of the ladder, and torque 2, which is force of gravity of the person, were both clockwise, whereas torque 3 is negative. Torque 3 is counterclockwise. So now we move this to the other side, and we have torque 1 plus torque 2 equals torque 3. Okay? So as long as you get from this step to here, it doesn't matter in terms of how much workings, show more rather than less. R1 F1 sine 37 plus R2 F2 sine 37 equals R3 F3 sine 53. So all I've done is taken the equation for torque and substituted in for each one of our givens in the problem. We have the force of gravity of the ladder, the painter, and the normal force of the wall. Common mistake here is to assume that all the angles are the same. Again, remember for a ladder question that the vertical forces are not at the same angle as ones that are to the horizontal. Okay, so now that we have our torque equation plugged in, we're going to put in all our numbers. So we got the ladder, 2.5 from the pivot, weight of the ladder, and sine 37, plus the person, which is 3 meters up the ladder, and their weight is 539. And that's sine 37 equals the full distance of the ladder times the normal force of the wall times sine 53. So we got 176.9 plus 973.1 equals 5 times the normal force of the wall times sine 53. So we divide both sides by 5 sine 53. And the 5's cancel and the sine 53 cancel. Just be careful to do the bottom number separately. So 1150.0 divided by 5.0 sine 53 equals force normal at the wall. And that is 287.99. Now you need to check your significant digits that you were given in the question. And we've been given 2 significant digits as the least number. So we need to round this number to 2 significant digits, and you get 290 newtons. Now, at this point, it feels like you should be done after doing all that work. However, if you go back to the question, it says, determine the forces exerted on the ladder by the ground and the wall. So we just found the force at the wall. Now we have 2 forces left to find at the ground. The good part about this is that there are only 2 forces here in the x direction. If this ladder is not moving, then those are equal. And there are 3 forces in the y direction, 2 of which we know, so the third one has to balance the other 2. So the last step is actually a lot less work. To find friction and the normal force at the ground, you have to do 2 F net statements because there's 2 forces. You have F net in the x to get one, and F net in the y to get the other. The x direction, there are only 2 forces, so friction will equal the normal force at the wall. That's what you just found. So friction, no calculation involved, 290. Now, F net and the y, there are 2 forces. There's one up, force normal at the ground, and then you have force of gravity of the ladder and force of gravity of the person. Save yourself the time though, because we have already calculated the 2 of these to get your torque. Force gravity of the ladder is 117.6. Force gravity of the person is 539. So with 2 significant digits, that should be G, we got 117.6 and 539. It's 656.6, and you need 2 significant digits. Force normal of the ground is 660.